Let's talk about overdetermined systems of linear equations. That means that we have more equations than we have unknowns. So far, we only talked about the case exactly the same number of equations as there are unknowns, and on top of that, the matrix is invertible, determinant is non-zero. Now we talk about overdetermined systems, and first I want to motivate where can such a question come from. Let's assume that we have, for example, 4 persons or 4 items placed on a straight line, and we want to find out what is the distance between these 4. So there are 3 distances. There's a distance x1 between the first item and the second item, and then a distance x2 and a distance x3, and we want to find these distances. And we will find out by measuring, but there are errors in these measures. And if there are errors, we can have an idea, a very simple idea. Instead of only taking these 3 measures, we take 3 more, in this example, 3 more measures. And so instead of measuring only x1, x2 and x3, we get also some more measures. This one is if there were no errors, x1 plus x2. This is x2 plus x3, and this is x1 plus x2 plus x3. So we say, okay, there are exact distances and there are measurements. And what may be the results? Please give me some answers. What were the results of the measuring? Maybe the result here was 1.1, the result here was 1.9, and the result here was maybe 3.2. And then adding these two, you should get 3.0. But due to the errors in the measures, maybe we get 3.1. And here, from these numbers, the sum is 5.1, but maybe we measured 4.9. If these were the measures, then we have 6 values, and we want to find out now x1, x2, and x3. What we measured, we can formulate as an overdetermined linear system. And what is this linear system? In this case, we have the following. x1 is 1.1, x2 we measured 1.9, and x3 we measured 3.2. x1 plus x2 we measured 3.1, x2 plus x3 we measured 4.9, and all these x1 plus x2 plus x3 we measured 6.0. So we can notate like that. Okay, so this is our matrix A, this is our unknown vector x, and this is our right hand side vector b. And what do we want? We want the solution of A times x is b, and we want to find an intelligent version of x. But what is the situation? It's impossible to find an x1, x2, x3 satisfying all these 6 equations, for example. Otherwise, this must not be 3.1, but this must be 3.0. And so we have contradictions in our problem. So we can reformulate here, and optimally would be some x which satisfies this equation, but this is not possible. So we can try to come as close as possible to this 0 vector, but we know we cannot get exactly 0. What does that mean? We have some difference, and then we can take the norm of that difference. And we want to find an x minimizing that norm. Which norm should we take? Let's say we take the Euclidean norm. The reason for that is that it's more easy to do the calculations, as we will see later. And instead of minimizing the norm, there we have a square root and we want to get rid of that square root. So let's square that. Minimizing the square root is the same than minimizing the square of the square root. So that's the reason for this square. Let's have a little example. Let's say we are here for that a and that b, and then one suggestion is maybe 1, 2, and 3. And then we can check what do we get here. So let's do so. And let's take the norm of that, and let's take the square of the norm of that. What do we get? We get 1 plus 0 plus 0, 1 minus 1.1, so minus 0.1. Then here we get 2 minus 1.9, so it's 0.1 positive. Then here we have 3 minus 3.2, so we have minus 0.2, and so on we get. And in the last row, 0. And what is the result? If we take the Euclidean norm, we have to square every entry and then take the square root. Okay. Then we have 0.1 squared, the minus is squared away, plus. And what is 0.1 squared? It's 0.01 plus once more, plus once more, plus once more. So we have 0.04, and the square of that is also 0.04, and adding that is 0.08. So this is the deviation. So let's test another choice of x1, x2, and x3. And let's say we test 1.1. Then we can redo that calculation. We only have to replace 1, 2, 3 by 1.1, 1.9, and 3.1. So we have that matrix times this time 1.1, 1.9, 3.1 minus that. And this time, what do we get? I did the calculations on my paper, and I strongly encourage you to do the same. Do these calculations as a little training, and if you do that, you get 0.04. Okay, so this is 0.04, and this is less than 0.08, and that means that this is a better choice than this was. So maybe this is the best choice, or let's check other solutions. It's not really a solution, it's something of a compromise. What is the best compromise instead of the best solution? And I prepared for that video, so I know the following. The best solution is, or the best approximation, the best compromise is. Okay, this was our example. And what is the natural question now? The natural question is how to find this best solution. So what can we say? There's some input vector and then there is some output number. So what do we have? We have a mapping. Input is Rn. In our example, n is 3, a 3 vector, and that is mapped to a number, a positive number, so we can also write like that. And how is that done? Given the input, the output is produced by that mapping, and this is the Euclidean norm. And so we have a function, and what do we want? We want to find the minimal value of that function, or not the minimal values, but the input which produces the minimal value. How can we find 0.1 squared plus 0.1 squared plus that and that and that? So we can take that vector, transpose it, and multiply it by itself. A vector transposed times the vector himself produces that sum. Okay, so that's a very good idea. So we can write the vector is that, and then we have to transpose, and then we have to multiply again with that vector. And so we can write like that. What is this? Transposed. There is a minus, so transpose each part. Here is a product, so transpose each part, but change the order. That's the way you transpose a product. So we have x transposed times a transposed minus b transposed. So this is that. And then we can multiply this times that. And how do we multiply? Multiply it each with each of them. And so we get that product, then we take that product, here we have a minus, then we have that, and then we have that, minus and minus is plus. What is the result? This is a number, this is a number, and this is a number, and this is also a number. Okay, each part is a number, but especially we want to focus on that and that. I want to say these two are equal. How can we do? If this is a number, we can transpose without changing anything. But if we transpose a product, then we transpose each part of the product and we reverse the order. So the order reversed is B transposed times A transposed transposed, which is A, times X transposed transposed is an X. So that means a number transposed does not change anything. If we transpose that, we get the same as we had here. So we can add these two by 2 times, and let's take that version. Okay, this is that part, and now let's copy these two parts. So now we want to continue our analysis, and it's not very much fun to do that for really general n. So let's assume that n is equal to 2, and if n is equal to 3, you can do every step more or less exactly as we do for 2 by 2, and nothing will change at all. But it's not much fun to do the notation for the general n, and we can introduce some notation. We want to introduce a notation for that. Let's notate K is the abbreviation for A transpose times A. Let's introduce something for that part. And let's introduce a notation for that. This is a number. And what is that? If n is 2, A is a matrix, a lot of rows, but 3 columns, 3 as many columns as there are unknowns. So if we transpose, we have n times something times a matrix something times n. So we have n, and in the case 2, we have a 2 by 2 matrix. For n is 3, then A transpose times A is a 3 by 3 matrix. So we can write, and this entry is not K21, but it's again K12, because a given matrix, whichever you want, A transpose times A will be a symmetric matrix, because if we transpose that, you get A transpose times A transpose transposed, which is the same as A transpose times A, and that means it's guaranteed constructing K in that way. This is a symmetric matrix, and so we have K12 also in that position. Then H is a vector, it's a row vector, and it has as many entries as we have n, and this is a number. And now let's rewrite that. X transposed is x1, x2, then this times x, then minus 2 times B transposed A, we introduced that notation, times x, and a plus c. And this is our function, and we want to find the minimum of that function. This is a function of two input arguments. The vector x consists in our case of two elements, x1, x2, and if you want to find the minimum, then the first step is find the partial derivatives and then set them to 0, and then you get a system of equations and you need the solution of that system. What are the partial derivatives? If we derive with respect to x1, then we get. But what should we do? First, we should rewrite that. Okay, too less space, so let's rewrite that. We have x1, x2 times, and now let's multiply this matrix times that vector. Then we get k11 times x1 plus k12 times x2. This is a column vector, and the first element, the element in the first position, is that. So these are not two entries, but only one. And in the second row, and if we multiply these two, then we get x1 times that, so x1 times parenthesis that part, plus x2 times parenthesis that part. Let's expand these parentheses, so we get k11 times x1 squared, this comes from that times that, plus x1 times here, so we have, and then plus k12 this, plus, and what do we have here? We have the same as we have here, so in total we have k11 times x1 squared plus 2 times that plus that. Okay, so now we take the partial derivative of that with respect of x1 here, and so let's derive. So we have 2 times k11 times x1 from this part, then here plus 2 times k12 times x2 plus nothing, and this shall be 0. But we forgot something. We forgot that part. Here we have 2 times h1 times x1, and the derivative of that is minus 2 times h1. Then let's take the partial derivative to respect of x2. Let's derive that. No contribution here. There's no x2 in that, so 0. Then we get 2 times k12 times x1 plus 2 times k22 times x2. And now we don't forget that part. We have minus 2 times h2 times x2. If we derive with respect of x2, we get minus 2 times that shall be 0. So now we have our system. This is our system. And how can we formulate? We can formulate as follows. Let's bring that to the right hand side. Let's bring that to the right hand side. And let's formulate as a system. So we have 2 times h1 and 2 times h2 on the right hand side coming from these. And here we can formulate, because that is a linear structure, we can formulate using a matrix. And the matrix is 2 times k11 and 2 times k12 for that. And here 2 times k12 and 2 times k22. And what do we see? We see a 2, a 2, a 2, a 2, a 2, a 2, and we see the original matrix K, K11, K12, K12, because it's symmetric, and K22. So we can write And now we can look what is K standing for. This is standing for A transposed times A times X vector, and this is B transposed times A. Okay, and that is very interesting. And this equation will always be this equation either way if we use n is 2 or 3 or 4 or 5. We proved it for n is equal to 2, but this is also, every step is a little more writing or even a lot of more writing, but in the end you will always get this equation. So why is that interesting? Because we started with that problem or with that problem, and here we have something very, very similar. Just a moment. H is B transpose times A, but here we have H transpose, so we have to transpose that, and that means change the order and transpose each part. B transpose transpose is B. So very interesting. We started with A times X is equal to B, and what did we get? A times X is equal to B, but the whole equation is multiplied from the left with A transposed. So this is a very surprising, easy structure. Let's summarize. If A is a something times n matrix, A transpose is a n times something matrix, n times something times n, so we get an n by n system. And here again, this situation, we have an n times 1 vector. And here we have also a n times 1 vector. So we are back in the situation of square matrices. This is a square matrix, this is a right-hand side, and we are looking for the solution of this system. For better understanding, we need an example. And we will use our example which we gave here. What was the problem? We had that system. And what is the solution? Satisfying that the solution is multiply by A transposed. So solve this matrix transposed is 1, 0, 0. That was the first row. It gets the first column and so on. And now copy the rest and multiply on the right hand side also with A transposed. And now let's multiply, so we get a 3 by 6 matrix multiplied by a 6 by 3 matrix. Result is a 3 by 3 matrix. The first entry here we get by doing that multiplication, and here we get a 1, 0, 0, 1, 0, 1. So we get a 3. Here this entry 0, 0, 0, 1, 0, 1, so we get a 2, and then 0, 0, 0, 0, 0, 1. And now this entry 0, 0, 0, 1, 0, 1, so this is a 2, but this matrix is a symmetric matrix. A transposed times A is always symmetric, because if we transpose, so it's A transpose times A transpose transpose times A. So A transpose times A transpose is the same as A transpose times A. So it's a symmetric matrix. So it was clear from the beginning that if we have a 2 here and this was correct, then this must be a 2 again. So this entry 0, 1, 0, 1, 1, 1. So in this case we get a 4. And this entry 0, 0, 0, 0, 1, 1. So we have a 2. This entry has to be 1. This entry has to be 2. And the last entry is 0, 0, 1, 0, 1, 1. So it's a 3. And on the right hand side we get 1.1 plus 3.1, which is 4.2, and 6, so we have 10.2. Then here 1.9, 5, 9.9, 15.9. And here we have 3.2, 8.1, 14.1. And now we have a square system and we need the solution of that system. This is not very much fun doing that by hand. So what can I do? I can ask Octave and then I will get an answer. Let's do so. So our A transpose times A, 3, 2, 1, 2, 4, 2, and 1, 2, 3. And then our right hand side, this is our H, 10.2, 15.9, and 14.1 transposed. So this is our input, and now find the solution of that linear system, and we get 1.125 and so on. And so this is our leveled out solution. That's the solution we wanted to find. But instead of doing that way, we could have also inputted our A matrix and our right hand side. So we get our product and also A transpose times B. That's our right hand side. But apart from that, we could also have used A/B, and then MATLAB learns that A is not a quadratic matrix but an overdetermined matrix, and then MATLAB and Octave says, okay, the user wants the leveled out solution, the solution in the sense we talked about, and then he gives us that answer. I don't think that this was a wise decision of MATLAB that you are allowed to use that syntax here, but this will be the topic of our next video. In that video I will talk about this command and why I think it's a risky decision which they have made. Okay, we found our solution, and this solution was 1.125. Okay, and this was our example, and now we are done. This was our video about systems of linear equations with more equations than there are variables.